Lesson 58, Explicit and Implicit Functions, Inverse Functions. So, as I said before I started the recording, not very calculus-y necessarily, just mathy tough stuff. Whether you remember them or not, we've talked about explicit and implicit before over the years. We've talked about inverse. Inverse you probably definitely remember a little bit more. I don't know if you remember your vocabulary for explicit and implicit, because that's really what it comes down to, is a little bit of vocabulary. So if you look there at the top, an equation that is written y equals or f of x equals are called explicit form. So hello? Okay. Yeah, they did. Yeah, if you can send someone down. They didn't tell me they were coming, so I don't have them. I didn't put them down there because I didn't know for sure if they were coming. So, okay, yep. If you can send someone down or come down, I can grab them real quick. Okay. Bye. Momentary pause. Is there anything else from that? There you go. You're quite welcome. Okay. Try this again. Restart. Okay, an equation that is written y equals or f of x equal is what we call explicit form. So the equation is explicitly solved y equals. This is the type that we put into our graphing calculator. If it's slope-intercept form, the nice form when we need it to be y equals for various things. Okay, an equation basically that is not solved y equals or f of x equals. So it states here an equation involving x and y, but not in explicit form, is called implicit form. When it's x's and y's mixed in together. So, for example, when we do derivatives and we talk about implicit differentiation, okay, that's the x's and y's are there together, and so we're taking the derivative with respect to x, with respect to y, implicit there. These equations can mean the same thing, yet look different. For example, a log equation, y equals log base 10x. This is your explicit form, it's y equals. But we also know, if you remember your log rules, we can do let's reverse here, but left, right, middle, and turn this into exponential form, 10 to the y equals x. This is no longer y equals, and so this is an implicit form. Equivalent equations, just two different forms. This would be the reverse. Exponential form is y equals 10 to the x. And basically, I would think of this as you take the log of both sides, and you end up with the log of y, and it'd be the log of 10 to the x, which is just x. Again, you could also think a reverse left, right, middle. Okay, so the equation could be explicit or implicit, but have the same meaning. Okay, so just a little bit of review about the vocabulary and the idea behind it. The other thing we're talking about today are inverse functions. It says we did inverse functions last year. We also did inverse functions back in Algebra 2. You might have even done them in Algebra 1. I don't know for sure on that one, but definitely in Algebra 2 I know we did them. So find the inverse of y equals 2x plus 4. What do you guys remember about finding inverses? You remember finding an inverse function? Huh?
I remember the word.
Remember the word? What's true about a function and its inverse? What's switched? Huh? The variables in terms of x and y are switched, right? I know it's been a while. You slept a lot since then, right? Hopefully you slept a lot since then. So inverse functions, in order to find an inverse, you switch x and y. So if we're trying to find the inverse of y equals 2x plus 4, one form of that inverse, y becomes x becomes y. So x equals 2y plus 4. This is what we would call the implicit form of the inverse. It's the form you always get first. Oh, I just need to scoot it up. I was seriously waiting for my recording to stop. It's just been one of those days. You know. Okay. And the recording didn't show it, right? Yeah. No, I knew you were trying to tell me something was wrong with the screen, but it wasn't clicking. Okay, so, and all I did there was underline. But the idea, the implicit, you switch x and y, right? Or the inverse, you switch x and y. So this is what we would call the implicit form. You're always getting the implicit form first. And then what is our job usually? We don't call it this, solve for y, right? Our job is to find the explicit form. We always say solve for y. So how do we solve for y?
Subtract 4 over and then divide both sides by 2.
Okay, subtract 4. When you subtract 4, we're going to have 2y equals x minus 4. Divide by 2, and we're going to have y equals, I'm going to say 1/2 x minus 2 if I divide each piece by 2. And I say that just because it puts me in a nice slope-intercept form. Okay, so implicit form of the inverse, explicit form of the inverse. Now, we also talked about this in maybe Algebra 2 and Pre-Calc. I know at least one of them. For any one-to-one function. So if a function is one-to-one, both of these are true in that the inverse composed with the function equals x, and the function composed with the inverse equals x. And I remember we talked about that because it was a way to prove if an equation and an inverse are truly inverses, that they will always make this true. They will always, when composed, will always equal x in both ways. Okay? So keep that in mind because we're going to talk about something down here in a little bit with it. So a couple of things. Oh, one other thing before we get to that example. The graph of a function and its inverse. We've talked about this because I talked about this with our exponential and our log function. They are reflections of each other across the line, y equals x. And the best example that I know you guys are familiar with is the exponential function and the log function. Okay? If we think about the exponential function, that is the function that runs along the x-axis, cuts up through 0, 1, and goes up there. Yes? That's our exponential function. Do you remember the log function? Log function runs along the y-axis, cuts through 1, 0, and goes over there. Now, since these are inverses, they are reflections in across the line y equals x. What's the line y equals x? It's that perfect diagonal line that goes through 0, 0, 1, 1, 2, 2, so on and so forth. Okay, so that's a good way to remember, when you think about your exponential function and your log function, how they relate. Okay? Okay, let's look at our one example here. And as I said, I'm going to add a second part here that's not exactly in the directions, but the example gives us a function, f of x equals 2x minus 3. Ask us to find f inverse of 4. What do? Okay, switch x and y and solve for y. And that is, of course, realizing that f of x is y, right? So really this equation is y equals 2x minus 3. If we switch it, it becomes x equals 2y minus 3. And then after I switch, solve for y. So if we're going to solve for y, what'd you guys do? Add 3. 2y equals x plus 3. Divide by 2. What's it look like when I divide by 2? Y equals 1/2 x plus 3/2. Or depending on the scenario, you could say x plus 3 over 2, but I like the 1/2 x plus 3/2. So officially, I've switched x and y, I've solved for y. This is my f inverse of x. So if I officially label, f inverse of x is 1/2 x plus 3/2. What did this problem ask me to do? Find f inverse of 4. How do I find f inverse of 4? Yeah, substitute 4 in for x. So 1/2 times 4 plus 3/2. Half of 4 is 2 plus 3/2. What is 2 as a fraction? 4/2 is important here. 4/2 plus 3/2 is 7/2. So f inverse of 4 is 7/2. That is definitely some algebra skills there, isn't it? Those algebra skills coming back to you a little bit? Okay, the other thing before I finish with notes today, the other thing I want to practice here is using this f of x and f inverse of x, and I want to prove that these are one-to-one and that this truly is a function and its inverse. So, in order to prove that this is one-to-one, what has to be true? What did it say up above? Yeah, when we do the compositions, the result is x. And so we're going to go through and do that. I'm going to do it over here on the right. Let me write down my original equation. F of x was 2x minus 3. And we decided f inverse of x was 1/2 x plus 3/2. And if it's one-to-one, it has to work both ways. So we need to test it both ways. So I usually start off finding f composed with f inverse of x first. Okay, so more algebra review here. How do we do f composed with f inverse of x?
In place of x and the f of x.
Yeah. Officially, I would write f of f inverse of x. And what it means is that we are plugging in f inverse into f. So f is 2x minus 3, right? So that's my function, 2x minus 3. So 2 times something minus 3. What am I putting in for x? Whatever f inverse is, which is 1/2 x plus 3/2. Do the math, right? Take the 2 and,
cancels out the fraction.
okay, cancels out the fraction, so distribute. 2 times 1/2 x is x plus 2 times 3/2. It's just 3, and we still have a minus 3 out there. What do you know about 3 minus 3? 0, and so we're just left with x. So is that what we wanted to happen? Yeah, that shows one-to-oneness. Again, if it truly works, it has to go the other way too. So the other way means we're doing f inverse composed with f of x. So reverse what I'm doing here, yes? This time, f inverse of f of x. So we're taking what? Okay. Yep. F plugging into f inverse. So my f inverse that I'm starting with is 1/2 x, whatever that is, plus 3/2. And so what am I plugging in for x there? Whatever f of x is, which is 2x minus 3. Distribute. 1/2 times 2x. 1/2 of 2x is going to be 1x minus 1/2 of 3, 3/2, and then we have the plus 3/2 out there. X minus 3/2 plus 3/2 is x. What did I just show? This function and its inverse are 1-to-1. Okay, I think that's all right. Yeah. As I said, not very calculus-y. More review-like. Yeah. I know you definitely saw this stuff in Algebra 2 because I had all you guys for Algebra 2, so very possibly saw a lot of it in Algebra 1, so.
Algebra 1 was too long.